So I want you to imagine for a second that you're standing at a really busy city intersection.
Okay, picturing it.
And the cellular network all around you isn't just, routing text messages or streaming music to your headphones. Instead, it's acting like this giant invisible radar system.
Right.
It's tracking the exact speed and trajectory of every single car, every bicycle, every pedestrian, all in real time. Basically mapping the physical environment down to the centimeter and doing it without a single camera.
Which sounds completely like sci-fi.
It does. But that is the actual documented promise of 6G technology. The thing is, though, if you look online today, you would think 6G is arriving like tomorrow morning to either magically merge our consciousness with AI or, completely fry our DNA.
Yeah, the hype is pretty wild right now.
It's totally off the rails. I mean, we are living in 2026. Most of us are just finally getting used to having a reliable 5G connection. So today, we are cutting through all of that noise. For you listening right now, our mission for this deep dive is to bypass the WhatsApp conspiracy memes, skip the utopian tech pitches, and just go straight to the actual source material.
Which is really the only way to understand what's actually happening.
All right. We're talking academic papers, official framework reports from telecom heavyweights like Ericsson, the International Telecommunication Union, the 3GPP, plus some really great analysis from industry veterans like Dean Bubbly.
Yeah, and the contrast between the internet's version of 6G and the actual engineering reality is just staggering. I mean, when you sit down with the real physics, the proposed spectrum bands, the deployment timelines, the real story of 6G is fundamentally a story about overcoming some extremely severe physical limitations.
Which is honestly so much more fascinating than the fake sci-fi stuff anyway.
Oh, absolutely. It's fascinating. But to get there, we have to dismantle a few of these really pervasive myths first.
Okay, so let's start with the loudest one right now, which is the timeline. There is this frantic narrative online that 6G is just this breakneck global sprint. Like any day now, the entire digital infrastructure of the world is going to just flip a switch and upgrade.
Right.
But looking at the ITU's IMT 2030 framework, or the 3GPP Release 21, the actual timeline is painfully slow. I mean, we are still in the very early stages of basic research and standardization.
Yeah, and that standardization phase is the massive bottleneck here. I mean, it's not just about some engineers designing a faster antenna in a closed lab somewhere.
Right, because it has to work everywhere.
Exactly. Before a single piece of commercial 6G equipment can even be manufactured, the entire global telecommunications ecosystem has to agree on a universal language.
Oh.
So we're talking about strictly defining the exact radio frequencies, the highly complex structure of the data packets, and all the precise protocols for cross-border network handoffs.
And that interoperability piece is notoriously complex.
Right.
Like if I have a device manufactured in South Korea and I'm roaming on a network in Germany,
Right.
and my phone needs to seamlessly hand off this ultra-high frequency signal from a big outdoor cell tower to some tiny indoor transmitter without dropping a single packet of data. The engineering required to just coordinate that across a dozen different hardware manufacturers is insane.
It's staggering. And it takes years of brutal, highly technical negotiations to finalize all of that. So according to the current 3GPP roadmaps and Ericsson's projections, we are not going to see those initial foundational standards locked in until the late 2020s.
Oh, wow.
Yeah. We might see some highly controlled pre-commercial showcase trials around 2028, maybe tied to a major global event like the Olympics or something. But a wide-scale commercial rollout, that is slated for 2030 at the absolute earliest.
Okay, so this is a deliberate incremental evolution.
Very incremental.
It's like someone promising you that a brand new flying car is going to be parked in your garage next week, when the reality is we are still in the middle of tuning up our 5G engines.
That's a perfect way to look at it. The 5G rollout is still ongoing. 6G is just the horizon.
Okay, so that brings down the second major fallacy we've been seeing, which is the idea that when 2030 finally rolls around, 6G is going to just instantly blanket the globe and make 5G, 4G, and Wi-Fi totally obsolete.
Right, the ubiquitous coverage myth.
Yeah. But industry analysts like Dean Bubbly and research firms like IDTechX, they are emphatic in these reports that 6G will not, and literally physically cannot, be ubiquitous.
No, it can't. And that all comes down to the spectrum allocation. Because to hit those crazy terabit speeds that 6G promises, telecom companies are looking at utilizing the sub-terahertz bands.
The sub-terahertz bands.
Right. And anyone who follows radio frequency physics knows that sub-terahertz bands have notorious propagation issues. You are dealing with millimeter-level wavelengths here.
Meaning they are incredibly fragile.
Extremely. So in radio physics, we deal with this really strict trade-off between capacity and distance. Lower frequencies, they penetrate structures easily, they travel for miles, but they carry a pretty limited amount of data.
Like 4G or even older 3G networks.
Exactly. But sub-terahertz frequencies, they can carry a mind-bending volume of data, but their wavelengths are so minuscule that they suffer from severe attenuation, meaning they get absorbed by almost anything in their physical path.
So what, like a brick wall?
A brick wall, heavy foliage, rain. Honestly, even just the ambient oxygen molecules and water vapor in the atmosphere will rapidly degrade a sub-terahertz signal.
That's crazy. It's like the difference between shining a wide floodlight that illuminates a whole field versus trying to shoot a really delicate laser pointer through a dense fog.
Yes.
The laser holds a tighter beam of information, but the absolute slightest obstruction just scatters it entirely.
That's exactly what happens.
So if I'm listening to this right now, I'm probably thinking about how my phone occasionally drops a 5G signal just because I walked from my living room into my kitchen.
Right, we've all been there.
So if sub-terahertz waves are that much more fragile, a 6G signal might only travel, what, a few hundred meters in an optimal real-world environment?
A few hundred meters if you're lucky, yeah.
So how on earth does the 3GPP propose building a reliable global network on something that is so easily blocked?
Well, the only engineering solution to that propagation problem is extreme densification.
Densification, meaning more towers.
A lot more towers. You cannot rely on a single, powerful macro cell tower to cover a 3-mile radius anymore. To maintain a continuous sub-terahertz 6G connection, you have to deploy transmitters on a completely unprecedented scale.
Oh, wow.
We are talking about base stations, on street lamps, on the corners of every building, dedicated indoor microtransmitters in every single corridor of an office complex.
But wait, the capital expenditure required for that level of densification must be astronomical. I mean, no telecom operator is going to blanket rural areas or even sprawling suburbs with that sheer density of hardware.
They won't. They absolutely won't. 6G is going to be deployed as a complementary layer in very specific high-demand environments.
Okay, so where will we actually see it?
You'll see it in dense urban financial districts, automated smart factories, university research campuses, maybe crowded stadiums. But as soon as you step outside of those highly optimized zones, your device will simply fall back to 5G, advanced Wi-Fi, or even satellite networks.
So 6G is just an additive layer for extreme performance. It's not a wholesale replacement for what we have.
Exactly. Not even close.
Okay, but if the physical infrastructure is that unbelievably expensive to deploy, and the signal itself is that fragile, the use case has to be spectacular to justify the investment.
Oh, it is.
Because the prevailing narrative online is that 6G is being built specifically because global artificial intelligence demands it. Like, the claim is that AI models simply won't be able to function or scale without a 6G backbone.
Right, and Dean Bubley's analysis targets this specific AI 6G linkage directly.
Yeah.
He points out that it is heavily, heavily overblown.
Really?
Yeah. The advanced AI we are utilizing today, and even the models projected for the near future, they operate remarkably well within the parameters of current 5G networks and edge computing architectures.
Right, because we already distribute the processing load to the edge anyway. We keep the AI inference close to the user rather than round-tripping every single prompt all the way back to a centralized cloud.
Exactly. And 5G is more than capable of handling that specific data transfer. 6G isn't some magical prerequisite for AI to function.
So what is the actual point then? If not AI, what justifies the billions of dollars?
The real capabilities that justify it lie in the leap from millisecond to microsecond latency,
Microsecond.
combined with terabit per second throughput. So 5G brought us into the low millisecond range, right? Which is honestly fast enough for basically any human interaction.
Right, we can stream video, play games.
Yeah. But 6G aims for microseconds. A millionth of a second.
That is, I mean, going from millisecond to microsecond latency, that fundamentally changes machine-to-machine trust.
Exactly. Because human reaction time sits around, what, 200 milliseconds?
Yeah, something like that.
So we don't notice the difference. But for a swarm of autonomous drones navigating a dense urban airspace together, or robotic arms coordinating on a remote surgical table, a microsecond response time entirely eliminates the margin of error.
It removes the latency bottleneck from complex real-time automation.
Yes. And it also unlocks high-fidelity real-time holography.
Okay, now we're talking sci-fi again.
A little bit, but we're not talking about a compressed, flat video feed. We are talking about rendering a fully realized, three-dimensional digital twin of a person or a complex mechanical part into a remote space.
Right.
And maintaining that volumetric data in real time without any jitter or lag as the subject moves, that requires moving colossal amounts of data with zero delay.
That is incredible.
It is, but arguably the most disruptive capability and the one that fundamentally shifts how we even define what a cellular network is ISAC, Integrated Sensing and Communication.
Yes, IAS. Okay, this is where the technology actually starts to sound like magic to me. Because sub-terahertz waves are so high frequency and so sensitive to physical obstructions, engineers have basically realized they can use that fragility as a feature.
Exactly. It's brilliant.
The network doesn't just transmit data packets back and forth. It actively analyzes how those radio waves scatter and bounce off physical objects in the environment.
Right, so the communication network effectively doubles as a highly sensitive radar system. With ISAC, the cellular infrastructure continuously maps its surroundings. It can detect the physical dimensions of an object, calculate its velocity, and monitor its trajectory in space.
So if we put this in a real-world scenario, in a smart city deployment, an ISAC-enabled intersection wouldn't just connect the cars to the internet.
Yeah.
The network itself would actually see a pedestrian stepping off the curb just based on how their body disrupts the ambient radio waves.
Yes.
And then it instantly transmits that spatial data to the collision avoidance system of an oncoming autonomous vehicle.
Precisely.
Yeah.
The car's onboard sensors wouldn't even need a direct line of sight to the pedestrian. The network itself provides a pervasive, real-time physical map of the intersection.
That is just wild.
And the applications extend way beyond just traffic management. According to the sources, we are looking at environmental sensing capable of measuring hyperlocal air quality or even tracking rainfall density just by analyzing how the water droplets absorb specific sub-terahertz frequencies.
Okay, that's really cool. But wait, I read something about healthcare applications too, right?
Oh yeah, in a healthcare setting, researchers are testing how ISAC can monitor a patient's breathing rate or even their heartbeat just by reading the microscopic disruptions in the ambient radio waves as their chest rises and falls.
Entirely contact-free.
Completely contact-free.
Okay, but listen, if you tell the general public that the brand new cellular network is effectively a ubiquitous, invisible radar system that's capable of tracking their physical movements and monitoring their heart rate through a wall,
Oh, the pushback is going to be massive.
it's going to be fierce. I mean, if the network can physically see me, people are naturally going to assume it is either surveilling them 24/7 or physically harming them, which seamlessly feeds right into the health fears and conspiracy theories we are seeing everywhere online right now.
Uh-huh.
People are claiming these frequencies cause severe cellular damage.
And look, the apprehension is logical when you're first presented with the idea of a pervasive sensing network. It sounds invasive. But the health fears require us to draw a very hard line between different types of physics.
Because it always comes back to the word radiation.
Exactly. The anxiety largely stems from a fundamental public misunderstanding of the word radiation, which simply describes the emission of energy.
Right. Visible light is radiation.
The warmth radiating from the Earth is radiation. The critical scientific distinction we have to make here is the boundary between ionizing and non-ionizing radiation.
Okay, break that down for us.
So ionizing radiation, like X-rays or extreme ultraviolet light, carries photons with enough kinetic energy to actually knock electrons out of their atomic orbits.
And that is the mechanical process that breaks chemical bonds, damages DNA, and leads to mutations or cancer.
Precisely. But 6G frequencies, even as they push into the sub-terahertz range, they remain firmly on the non-ionizing side of the electromagnetic spectrum.
Okay.
The photons in these specific radio waves physically lack the energy required to break chemical bonds. They literally cannot alter DNA. The primary documented interaction they have with human tissue is just a very negligible heating effect at the surface of the skin.
The caveat, though, looking at the literature we reviewed, is that consumer technology has not historically utilized sub-terahertz bands at this kind of scale before.
That's true.
So we don't have, like, decades of long-term epidemiological studies on continuous human exposure to these specific frequencies.
And that is a totally necessary scientific caveat, right?
Okay.
Long-term data collection is always required for novel tech deployments. However, organizations like the World Health Organization and the International Commission on Non-Ionizing Radiation Protection, the ICNIRP, they continuously evaluate the available data. and the limited controlled studies conducted on sub-terahertz frequencies to date operate under incredibly strict safety thresholds.
So what's the verdict right now?
Currently, there is zero conclusive, peer-reviewed evidence of adverse health effects when the technology operates within those established international safety limits.
So the hysteria we are seeing on social media is essentially just the exact same script used during the 5G rollout, just updated with the number 6.
Exactly. The physics of non-ionizing radiation haven't magically changed in the last few years.
Honestly, considering the intense cortisol spikes people get from doom-scrolling these conspiracies all night, the stress is doing far more measurable damage to their bodies than a 6G antenna ever could.
It really is. And the worst part is it distracts from the actual complex real-world challenges that engineers and policymakers are actively struggling with. While the internet is arguing over imaginary DNA damage, the telecom industry is facing a series of truly daunting logistical and geopolitical hurdles to make this 2030 timeline a reality.
Let's talk about those real hurdles, starting with the infrastructure requirement,
Yeah.
because that alone threatens to severely widen the global digital divide.
Unquestionably.
If the propagation issues of sub-terahertz waves demand tens of billions of new microtransmitters, the deployment economics only make sense in highly lucrative, hyper-dense urban centers.
Right. Telecom operators are businesses. They're not going to invest billions of dollars to lay fiber backhaul and install dense transmitter arrays in rural communities or developing nations. It just won't happen.
So we risk creating this heavily tiered global reality.
Exactly. Wealthy urban centers will have access to microsecond latency automation, advanced ISAC logistics, real-time remote healthcare, while vast portions of the globe are just left utilizing aging legacy networks.
The economic and social inequalities that creates are profound.
They are. And on top of that, powering that new infrastructure introduces a massive environmental hurdle.
Right, because you're taking a network that already consumes a huge amount of electricity globally, and you're layering on tens of billions of new transmitters, all of them continuously pushing terabits of data and running complex edge computing algorithms to interpret that ISAC radar backscatter in real time.
The energy footprint is staggering. Engineers have to figure out how to dramatically increase the power efficiency of the hardware itself, or the rollout of 6G will directly conflict with global carbon reduction targets.
Because we cannot power a next-generation network by just burning more coal.
No, we really can't.
And then there is also the privacy nightmare inherent to ISAC.
Oh, yes.
I mean, if the cellular network is constantly mapping physical spaces, it is generating a persistent, real-time spatial record of human movement. If a bad actor breaches a traditional 4G or 5G network, they might steal financial data or private communications. But if they breach an ISAC-enabled 6G network, they potentially gain access to a live, physical 3D map of a private home or a secure government facility.
It's a totally different threat level. The cybersecurity architecture has to be absolutely flawless before this ever goes commercial.
Which is exactly why the standardization process we discussed earlier is not merely just some dry technical exercise. It is currently the center of a fierce geopolitical battle.
It really is. Setting the global standards and, more importantly, controlling the underlying patents for these technologies is a matter of profound national security and economic dominance.
Right. Looking at the dynamics detailed in these reports between the United States, the European Union, and China, the race isn't really just about who builds the fastest hardware first. It is about who secures the standard essential patents, the SEPs.
Right, the SIPs. Because if a nation's domestic telecom sector can successfully lobby the ITU and the 3GPP to adopt their specific technical frameworks for, say, sub-terahertz packet routing or ISAS security protocols,
Then they basically hold the keys to the kingdom.
exactly. Every other manufacturer on Earth will have to license their intellectual property just to build compatible devices.
So we are seeing different blocs taking highly strategic approaches to this. Some countries are heavily subsidizing state-backed telecom champions to basically flood the standards bodies with technical proposals,
Right.
while others are trying to build open vendor-neutral architectures to kind of dilute the power of those proprietary hardware monopolies. And look, we aren't here to evaluate which geopolitical strategy is superior, but we absolutely have to acknowledge that the friction is real.
Oh, it's very real. And the danger is, if diplomacy fails and the standards process fractures, we could end up with regionalized, totally incompatible 6G networks.
Which would effectively roll back decades of global interconnectivity. So let's try to distill all this for you, the listener. If you take away anything from our dive into these sources today, it should be that 6G is strictly bound by the rigid laws of physics.
It is not magic.
It's not magic. It is an exciting evolution aimed for the 2030s, offering terabit speeds, microsecond latency, and revolutionary sensing capabilities that essentially turn the network into an environmental radar.
But because those high-frequency waves are so incredibly delicate, 6G will not replace our existing networks overnight.
Right. It requires a staggeringly expensive, energy-intensive densification of our physical infrastructure. And it relies on a very delicate consensus among global powers to even get off the drawing board in the first place.
The real threats here are not non-ionizing radio waves.
No.
The real threats are the widening digital divide, the environmental cost of extreme data consumption, and the immense cybersecurity challenges of a network that literally senses its physical environment.
Which leaves a final, lingering question to consider. We outlined how these sub-terahertz networks require tens of billions of new transmitters, right? And how the energy consumption to run that dense infrastructure is one of the most critical ethical and environmental hurdles facing the 3G IP today.
Because the raw electricity required to sustain that level of continuous data processing and transmission is just immense.
Immense. So, considering all the intense geopolitical maneuvering over patents and standards, is it possible that the true global race for 6G dominance won't actually be won by the nation with the best telecommunications architecture?
What do you mean?
Well, what if the real race is simply about who can generate the massive, unprecedented amounts of sustainable energy required to just keep the network turned on?
Wow.
Like, we might be hyper-focused on designing the ultimate flying car without realizing we haven't secured the fuel to actually get it off the ground.
That completely reorients the entire conversation, from telecom engineering straight to energy infrastructure.
It really does. Thank you for taking this deep dive with us today. Keep your curiosity sharp, question the hype, look at the underlying mechanisms, and maybe double-check the physics before sharing those WhatsApp memes. We will catch you on the next one.